Good morning. Morning. I'm Bill Grubb, IEEE Computer Society President, and I welcome you to this session with presentations from our 3 Society Award winners. And since you're here to hear them, let us start right away by welcoming Ian Foster, winner of the ACM IEEE Computer Society Ken Kennedy Award.
Hey, good morning, everyone. Thanks for getting up so early. I really appreciate it. I'll just talk briefly, say first of all, it's a great honor to receive this award, which I wanted to emphasize is certainly on the behalf of my work, but of so many wonderful colleagues and collaborators. I'm going to acknowledge some of them explicitly, but there are many more than I can recognize. So I've had the privilege of working with wonderful people. So I thought I might start with a little bit of a little retrospective of my life from the perspective of this SC conference. So if you look on the left here, you can see me. That's me arriving in Chicago in early 1989 at Argonne. Was then and still is a wonderful place. I had the, by the way, Jack Dongara had just left for Tennessee at that point. I don't know whether that was a coincidence, but he did. And I had the privilege and pleasure of joining soon after I got to Argonne this new Center for Research on Parallel Computation, an NSF Science and Technology Center led by Ken Kennedy. And under Ken's leadership, CRPC was really a remarkably collegial and productive community. A great place to work. And Ken was also very supportive of me and other early career researchers. For me, he provided some resources that allowed me to recruit a young 22-year-old hotshot, Steve Tiki, who I then worked with for 30 years until he sadly passed away just 3 years ago. And much of what I'm going to talk about today was developed with Steve. So I'll dedicate this talk to him. But back to SC. So over 30 years, I've had 30 papers accepted at this conference. Ups and downs, but here are the faces of the 91 of my 97 co-authors who I could find pictures for. Time is too short to call them out by name, but what exceptional people. Really, I think what makes HBC such a wonderful field to work in is the wonderful people that we get to interact with. You can probably recognize some of the people in those pictures. Quite a few of these people were students or postdocs at the time of the paper, so these are their pictures as well. So you might think, wow, this fellow and his colleagues, they published 30 papers in 30 years. They're clearly very good at writing papers that the SC reviewers really like. But I got some additional data from Mark Montague from Linklinks. These are all the papers we submitted from 2011 onwards. And you can see we didn't always hit it out of the park. And actually, I'm a data scientist. I know some AI techniques. So I applied an advanced method called linear regression to our acceptance rates. And I can determine that my last paper to be accepted at SC will be next year. And only if I submit like 20 of them. So big challenge. Okay, so let's get on to the topic of the talk. The theme of my talk is better information faster. This is something I've always been fascinated by. How do we use computing to deliver better information faster to decision makers? And I think maybe I've been interested in this perhaps because of where I grew up in New Zealand, which is a long way from anywhere, and information gets there, at least back in the day, fairly slowly. And in fact, when I left New Zealand back in 1980, it took me 90 days to get to North America. I had this idiosyncratic idea of going by sailboat, which was very fun but rather slow. Now, of course, we can transmit information much faster, 90 milliseconds from New Zealand to Dallas, right to the hotel. I ran ping to test that. So that's about 100 million times faster, which is great. But it's still quite slow for many purposes, and not something we can improve further directly, because of course that's the speed of light limit that we're facing. So it's maybe let's look briefly at what's involved in obtaining useful information. So straightforwardly, simplistically, we send a message to request an answer to some question that requires some computation, perhaps, and the result comes back. So, the time required to get that answer is going to depend on things like the number of operations we have to perform, the data communication costs, the distance to be traversed, the speeds at which we compute and communicate, and a few other things. So we can express that in terms of this nice formula. And then we can talk about how we might go about accelerating that. And there's all sorts of techniques we can use. We can use better algorithms to perform fewer operations. We can use faster computers. We can use faster networks, et cetera, et cetera. And my colleagues and I have been working to optimize various of these things for many years. I'll mention just a few of the things that we've been doing. So one is working to perform many different things at once, so when we send questions, we can get answers faster. Back in the day, not that long ago really, supercomputers were used only for what people called single program multiple data, or SPMD, computations. A bit of a straitjacket, and so to escape this straitjacket, we've worked for quite a few years on new methods and tools that allow us to perform many different things at the same time, task parallel or heterogeneous computing. Things like Strand, Swift, Parcel, most recently Colmena. These are projects, of course, that were done with quite a few different people. For example, Kyle Chard and Dan Katz and others for Parcel, Mike Wild and Justin Wozniak for Swift, and then Logan Ward for Colmena. So nowadays, these sorts of applications are pretty mainstream. And in fact, if we look at some of the Gordon Bell Prize winners, many of them are doing these interesting things like using AI to guide ensembles of simulations. But that didn't used to be the case, and I think we had some role in pushing that forward. Another area of great interest is how we can accelerate scientific discovery processes by providing what we call managed research acceleration services. So I'm going to start a little video here, but what I'm talking about in this case is Globus, a service that runs on the Amazon cloud but manages data movement across wide area and local area networks. And what we're seeing here is, if you look at carefully, it's sort of an interesting graph. X-axis is the great circle distance from source to destination. Y-axis is transfer size. And there's a few extra pieces of data flipping by there. So this is showing all large transfers performed with Globus over about 12 years. Among the nowadays more than 40,000 endpoints that are located worldwide. And if you watch it, it's sort of fun. You see, first of all, a small number of transfers in the United States primarily, then more and more reaching long distances, and ultimately, and also getting faster, getting pinker and pinker. You notice that I'm using the SC conference colors here, as someone pointed out. So this is what we call a managed research acceleration service, and our belief, and I think we've demonstrated this is that we're able to make a substantial difference in how fast people can address complex problems by providing these sorts of resources. Two other things. You'll notice there's a big gap in the middle. Sort of weird. No one transmits 5,000 kilometers, or very few people. Well, it turns out that's because the Atlantic Ocean gets in the way. So there aren't many places that are exactly 5,000 kilometers apart. And then you'll see on the far right one it's at 19,855 kilometers. So someone said to me, is the world really that big? Well, it turns out it is. The circumference of the Earth, the semi-circumference, is about 20,000 kilometers. The distance from Madrid, Spain, to Wellington, New Zealand, which is what these transfers were, is just slightly less than that. And growing up in New Zealand, we knew that we lived in the Antipodes, and this is a demonstration of that is indeed the case. There are basically two cities that are about as far apart on the world as you can get, and we're moving data back and forth between those locations. Okay, let's move on and sort of more to this question of computing in the continuum, which is the title of my talk. So Jack talked yesterday about how computers have got ever faster, which of course we know well. Over that same time, other things have happened, of course. Also, networks have got much faster, but they've also become far more reliable and integrated. So we can now think of a world in which barriers to remote computing are essentially eliminated, apart from the speed of light, of course, which is still a significant constraint. So we can access computation remotely as easily as we can locally. So we can start to talk about a computing continuum, a continuum of locations, a continuum of performances, and the choices that we then may want to make in order to choose where to execute. So say a little bit about communication. Here I show a couple of technologies that are advancing our ability to communicate to anywhere, eliminating the white spaces in our communication maps. Of course, 5G and 6G networks, but also really exciting is work that's been done on coherent life free space optics, or I think the popular term is space lasers. So this is a picture from the website of a company, IEEE, which is a Google spin-out, which is building communication networks based on this sort of technology. They call their platform space-time. Originally, it was called Minkowski. Minkowski, of course, was a fellow who worked with Einstein and observed about the special theory of relativity, that it defined a space-time continuum such that space and time were sort of interchangeable and could not be talked about each in isolation. And nowadays we might start to think about, with universal high-speed communications, we can adapt his words, misattribute them, to talk about location and speed. So the speed of a computer as perceived by a user is not an absolute, but it depends on where the computer is located. A farther away computer may be faster or slower than one local, depending on its performance and its distance and other such things. So to show what that means in practice, I'll give a couple of examples. So I heard a nice talk by Nan Tran from Fermilab recently. He talked about he's working to accelerate trigger analysis computations for high-energy physics. And he speeds it up from 2,000 to 50 milliseconds by running it on an FPGA, straightforward sort of thing. But it turns out the FPGA is actually located in an Amazon data center in Virginia. But that doesn't matter. That's only 10 milliseconds away. So he speeds it up from 2,000 to 50 milliseconds with 30 milliseconds for computation and 20 for communication. So the net result is a 40 times acceleration. Another example, this is involving work by Zhenchang Liu and others at Argonne and SLAC, high-energy diffraction microscopy experiments at the LINAC coherent light source. They use a deep neural network to accelerate the detection of interesting features. That runs on a GPU at SLAC, but the GPU is not fast enough to retrain the model periodically, as is required to deal with structural deformation in the sample. So what do? Instead, we dispatch the data and the training task to a Cerebras CS2 deep learning supercomputer at Argonne National Lab, which can do the whole thing can train in 19 seconds, move the data back and forth in 12 seconds, again, a 35 times speed up. So I think we're going to see more and more of these sorts of trade-offs going forward. So here we've got a few. We're using a neural network to accelerate computation. We're streaming data. We're using parallelism at the computer. We're using specialized hardware. We're using data center AI systems. And then we're leveraging work done by ESNet to accelerate communication rates and reduce latency, and work at the Argonne Leadership Computing Facility to deploy these specialized computers. So, in general, I think to accelerate our computations, we need to be able to, we're going to be modifying our applications, modifying our system software, modifying and defining the hardware on which things run. So we've got a wonderfully complex codesign problem, which we are going to be presumably working out over the next several years as we start to build computing continuum systems that encompass more than just a few supercomputer centers. And of course, that's why this work is so much fun. What I'll talk about for the remainder of my time now is how do we make it possible for people to conduct these sorts of co-design and application continuum computing experiments. We need new methods and tools that will allow us to easily retarget applications to different computers in a distributed computing environment. We need ways of expressing these distributed continuum applications. We need means of accessing data regardless of where we're located, and of managing trust and in the context of large numbers of resources that may be managed by different people. So we've identified the following 4 key requirements that have to be addressed to enable these experiments. I'm sure there are others, but these are the 4 we've chosen to focus on. The means of developing applications, the ability to compute anywhere, access data anywhere, and ensure only authorized operations occur in appropriate locations. And we're exploring ways of addressing these questions, allowing people to express flows that link across resources, and then new managed research acceleration systems beyond Globus transfer that allow us to manage flows, manage computations, and manage authorization and credentials. And as I may remind you, these managed research acceleration services like the Globus transfer service, the key idea is you use cloud management for ultra-high reliability, and then this global footprint of endpoints. We've got 40,000 Globus endpoints. We want to have similar numbers of FuncX and Flow endpoints to provide impact directly at the level of scientists. Okay, so a few words about each. So flows is a first element of this. We've been developing a wonderful group in the Globus team at Argonne and the University of Chicago has been developing methods that allow us to express very easily simple series of operations. You can also have choices and so forth, but I won't go into that. So here's one, for example, associated with the high-energy diffraction microscopy application. So we're going to be transferring data to a model test bed. We're going to be preparing the data, training the model, redeploying the model back to the location at SLAC. And then we're going to provide these research acceleration services that are for the management of the resulting computations. And they will combine events, new data is available. Well, move it to the AI accelerator. It arrives there, train the model. The model is finished, move it back for deployment. And I show a little screenshot of the sorts of tools that the Globus team has developed to manage these things. Second element, a project that's really very much led by Kyle Chard and Dan Katz, FuncX. So we need to be able to do more than move data. We've got to be able to run computations, and we want to be able to run computations anywhere where computation is required. It might be at a beamline or an experiment, at some intermediate point at a national supercomputer center. We need a way of abstracting computation so we can dispatch requests at any time to perform computation. And this is something we've been trying to do for decades, and we're now at the point where we really can do it. It's very exciting. So FuncX will allow you to turn any compute system into a managed, globally accessible endpoint. Could be a powerful supercomputer like Aurora, We already have some racks up, by the way, so we're doing that. Don't listen to that Dongara guy. No, so or a laptop or an edge device and so forth. And then you can, with a few lines of code, deploy this agent on one of those computers. You can register functions, another few lines of code, and then run the functions with additional lines of code. And really exciting. And then we can take these, armed with the flow service and this FuncX universal computing environment, we can then start to take a rich variety of flows and run them, modifying where things happen and exploring the implications of different policies. So here I show 7 flows that are in use at the Advanced Photon Source. That's a synchrotron light source at Argonne National Lab. You probably can't see the fine print here, but they range from X-ray photon correlation spectroscopy to the high-energy diffraction microscopy we've already seen. Serial synchrotron crystallography is used for COVID protein structure determination and a variety of others. And then we can see what happens when we run these flows. These are running routinely now, thousands of instances per month in some cases. And what I show here is the averaged performance over thousands of runs, in this case, performing all the computations at the Argonne Leadership Computing Facilities Theta system, and increasingly now the Polaris system also. And you show in orange the computes steps, blue is transfer steps, and there's a few other things like catalog management. And so you'll see the computations can be fairly long. They range from a few seconds up to hours. There is some transfer costs involved, but overall, we're getting significant acceleration by dispatching our computational tasks to remote places. And the key thing is, because we're using these cloud-hosted research acceleration services to manage everything, this runs reliably. Under the covers, there's one more element which most of us probably don't like to think about, but really important. We're running in this context where we want to be able to send requests to any computer anywhere, but we have to do that in a very carefully secured manner. I only want a flow that I start to run computations on resources that I've explicitly granted authority for the flow to run on. Plus, of course, the resource owner will also have their own concerns. So Globus Auth is this wonderful platform developed by Rachana Ananthakrishnan and a number of others in the Globus team, which addresses those concerns, allows us to express who do I trust to act on my behalf, and where is that person? What do I trust them to do? Where are they allowed to access? And I guess I shouldn't really have animated this, but I did. It's basically showing how we can step through a flow, and at each step there's an explicit verification of authority to perform operations using consent and token mechanisms. And as I show down the bottom left here, this has been running for quite a while. We've issued 1.3 billion access tokens since Globus Auth was started. So here's one interesting question. I think we've been building these tools. Now we want people to deploy them, and we're starting to see large facilities deploy them at some scale. This shows, for example, what's going on at the Advanced Photon Source. So we have maybe a representative example. So the APS has like 80 beamlines. We've got Globus agents deployed at many of them, FuncX agents deployed on all of the computers, and then these thousands of flows running routinely. Ben Brown at DOE talks about an integrated research infrastructure. So I think this represents a step towards the realization of such a integrated research infrastructure. And we're very excited to be seeing it actually working in practice. So someone asked me when I was preparing this talk, what does this have to do with grid computing? You did that 30 years ago or so. And so I think it's interesting to talk about that a little bit. Dan Reed, some of us know well, he has observed that computing differs from other sciences in that in computing, the questions stay the same, but the answers change over time. And I think that's very true in this case, right? So we're in a sense asking the same questions. How do we empower discovery by providing on-demand access to computing? But we're able to do it far better because now we have this ubiquitous communication substrate and far better ways of doing remote computing. There's still new things that we have to deal with. Actually, many questions that I won't spend time talking about, but I've listed a few of them here that hopefully we can all spend some time talking about. How do we reinvent various aspects of our computing environment and the way we develop applications in the light of these questions? Okay, well, thank you very much. To learn more about what we're doing, go here. Globus Labs is our research group, which I run jointly with Kyle Chard, and the Globus team, of course, is eager to help you with other things. Yeah, I should acknowledge finally the BRAID project funded by DOE. That's allowing us to explore these flow deployments. Thank you very much.
Thank you, Ian. That's a wonderful talk. We have time for a few questions. I'm trying to monitor the Slido here. We also have microphones. If you have a question, please go to the microphone. Let's see. And then also, anybody who's been up here knows that the lights are really bright. So, question? There? Yes.
Yeah.
Cleve.
You need to go to the
Mike. We need a mic.
Oh, well, maybe.
Well, so Ian will repeat your question.
Yeah.
One word, latency.
Latency.
Talk about rate. Latency is important. Establishing the connection.
Absolutely, latency is important, and my formula did have latency in that. The distance was one term, and that's of course really vital. Although it is amazing with the right applications and the right networks how much you can compensate for high latency. I think that's an exciting development. When your networks are ultra reliable, it still will take you 40 milliseconds to get from one side of the country to another, but you can be streaming the data at line rate, and in many cases that's satisfactory.
Yes. There, yes.
Hi Ian, Alex Josup, Vrije Universiteit Amsterdam. Great talk, really inspiring. I don't know if you can hear me.
No.
I can.
All right. So my question is, seeing all these results over so many decades, how can we actually get the entire community to be able to achieve similar results so that we don't have only one flower that doesn't make a spring, but a lot of different flowers, a lot of Ian Fosters?
It sounds a bit scary, I think, a lot of Ian Fosters.
Not referring to clones.
Yeah, so my view has always been we build tools that allow others to build on. And of course, in some cases, sort of MPI is a wonderful example. That's a specification. There are a couple of implementations. Those are tools that have allowed a vast community of HPC people to flourish. Similarly, I think our Globus service and some of our other things have been used by very large numbers of people. We have 300,000 registered users. So those are people who can then go on and do other more interesting things than running these basic services. So I think we've got to raise the level of abstraction. So at the moment, too many people spend too much time resolving problems that have already been solved. And you might get a paper out of it and a master's thesis, but it's not really advancing the science.
Yep.
Yeah.
Thank you.
Thank you.
We have a last question
Yeah.
for time online. What are the mechanisms necessary to provide the replication and failover needed to assess durability and availability?
Can I just read it again? Yeah, I think I got it. Yeah, so the question is about how do we ensure durability and reliability via, for example, replication. So in a sense, we're leveraging some of that from cloud providers who have thought very hard about these questions. But the science itself requires similar mechanisms. And I think, again, providing these core building blocks gives us a good, steady foundation on which to build, but now we need to be exploring these things. You know, if we're going to deliver vast amounts of climate simulation data, for example, to the community, we can't rely on people having to fiddle around and find the site that's currently available. We've got to make it trivial for that to be performed automatically.
Great. Okay. Let's thank Ian again.
Thank you.